Okay, so we've developed all of the areas in terms of the atomic structure, charge, and we're going to see now how charge leads to current and voltage. So we need to look at two areas that are going to be very, very important that you understand the measures of voltage and current and how to differentiate between them. Okay, characteristics, the mathematical relationships defining the unit of voltage, and describe the basic sources of voltage. So as we look at voltage and develop its mathematical relationships, we need to understand that we assign a unit to it called the volt. The volt then is a difference in potential energy per charge in electrical terms, and we call it voltage, or we use the capital V. You're going to see later as you get into the more advanced courses, we're going to use a little v, and we may represent it with units of time. Voltage then is defined as energy or work per unit charge. Okay, so if we look at the very basic definition, we've got work or energy in the numerator and a per unit of charge of Q in the denominator. Okay, so this is a mathematical relationships that gives you the basic fundamentals or constructs of voltage. Work then is expressed in joules. Charge, or Q, is measured in coulombs. So where joule is the energy measurement for a unit of work, we can take it all the way back down to, and this is something that you'll learn in your physics course, that a joule is equal to a Newton meter, and that Newton meter breaks down even further to the fundamental units of a kilogram times a meter times a second squared. Okay, so, and we multiply that times a meter. Okay, so we've gotten meters, kilograms, seconds squared. So we have kilogram meters squared per second squared. If you're familiar with it, this meters per second squared that we've got right here, that's actually acceleration. And we'll learn a little bit more as you progress through the program, how acceleration plays out in our units. So 1 volt then is the potential difference, the voltage, between 2 points when 1 joule of energy is used to move 1 coulomb of charge from one point to the other. So you notice we are putting this together in terms of a unit, and that unit is 1. So we have a basic unit that we can understand what's going on. Potential difference between 2 points when 1 joule of energy is used to move 1 coulomb of charge from one point to another. So let's look at the mathematical relationship that we just defined in the previous slide. If we have 50 joules of energy available for every 10 coulombs of charge, what's the voltage? So we set this up mathematically. Work per unit charge, 50 joules, 10 coulombs, and that gives us now our new unit of voltage of 5 volts. How do we get voltage? Well, we can get voltage in a number of ways. Batteries, solar cells, a generator, or an electronic power supply. Batteries you're well familiar with, in your flashlight, in your phone. A source of electrical potential energy that converts chemical energy into electrical energy. We call this electromotive force. And we have a relationship that we can form of series versus parallel. Solar cells then are based on something called a photovoltaic effect. 2 layers of semiconductor material then are formed in a photocell, and the reaction that occurs when the light hits it is that photovoltaic effect on a semiconductor. A generator converts mechanical energy into electrical energy using the electromagnetic induction. Again, we will explore that further in the future. And then an electronic power supply converts AC to DC from the wall current. These are your typical wall warts, same thing that you use to charge your phone. So we've defined voltage. We've looked at what a unit of voltage is comprised of. Let's look at an example. How much is the voltage when there are 24 joules of energy for 10 coulombs of charge. Again, we put it back into our relationship, work over charge, 24 joules divided by 10 coulombs gives us 2.4 volts, or almost 2.5 volts. Okay, we've also looked at the 4 sources of examples for voltage. The next area we're going to cover is current. Current and voltage are not the same thing. Think of current as water going through a water hose. That is the amount of flow that is occurring as the electrons pass down the wire. So it's the same thing as the water moving through a hose. So we've got movement of electrons. We're again going to have a formula, and then we're going to name and define the units. So electrical current then is a rate of flow of charge. Current in a conductive material then is determined by the number of electrons, the amount of charge that flows past a given point in a unit of time. So now we have a rate. Anytime you see time in the denominator, we've got a rate. So current is clearly a rate where voltage was not. Voltage was energy per coulombs. Now we've got charge per unit of time. Current is measured in a unit called the ampere or the amp, and we typically use the letter A for the shortcut designation. So let's look at the definition. 1 ampere is the amount of current that exists when a number of electrons having a total charge of 1 coulomb move through a given cross-sectional area in one point in time. So now what we've got here is, you can think of a wall or a barrier. What we're looking at is how much charge moves from this side of the barrier to this side of the barrier. So we create a cross-sectional area, and that allows us to define what current is. So in an example, 10 coulombs of charge flows past a given point in a wire in 2 seconds. Okay, so we've got our setup for the rate. What is the current in the amperes? So current is equal to charge divided by per unit of time. We've got 10 coulombs of charge, and we want to measure how much current flows past that point in 2 seconds. So 2 divided into 10 gives us now the new unit, coulombs per second, or 5 amps. And another problem, if there are 8 amps of current that flows through a filament in a lamp, how many coulombs of charge moves through the filament in 1.5 seconds? So now we're going to take that basic formula, I equals Q over T, and we're going to rearrange the terms. Okay, this is something we do a lot in electronics and in your math for electronics. So now what we need to do is leave Q in the numerator and move that unit of time out of the denominator and into the numerator on the other side, multiplying it times current. So we were given 8 amps of current. We want to know how much charge there is in 1.5 seconds. So 1.5 times 8 gives us back now 12 coulombs of charge. Okay, so we've looked at voltage and now current. We've defined current and stated its unit. We need to know then how many electrons make up 1 coulomb of charge. Let's correct this. How? There we go. So the relationships, we go back to our electrons per coulomb, 6.25 times 10 to the 19th electrons per coulomb. Okay, so what is the current in amps when 20 coulombs flow past a point in wire in 4 seconds? So 20 coulombs divided by 4 seconds gives us 5 amps. Okay, so the next one, a little more involved here. Now we're going to take a look at the relationship that current and voltage forms to give us a new unit of resistance. What is going on when we impede the flow of electrons through a material or through a circuit?